Okay, perfect. So I'll just get going. As Stravos just said, I'm Mihaela. I'm a research engineer at DeepMind and a PhD student at UCL, and I'm really interested in learning probability distributions and specifically doing so using deep learning methods. And this is what I'm going to talk about today. So of course, one thing to start with is that this is just one view of the field. There are many others, and I do have citations on the slides. And if you want to look at related papers, you can use something as connectedpapers.com to find related work. So let's talk first about the problem statement. So throughout this talk, I'm going to try to look at approaches to solve the following problem. We're trying to learn a model of a true underlying and unknown data distribution P star of X from a set of samples that we have, which in machine learning we often call our data set. So we will have X1 up to Xn from our true data distribution. And what we want to do is to learn a model of this distribution. And let's say this is just a very simple example of 1D data. Of course, in machine learning, we're often concerned with very high dimensional data. Often our data has millions of dimensions if we think, for example, of high dimensional images. And I'm going to show some examples of that in a bit. But just for the sake of illustration, I'm going to use this example of this 1D data set generated from a mixture of two Gaussians. And one question that we might have is, well, why are we interested in this problem? Well, once we have a model, once we have this distribution, we can query it to ask, well, what is the likelihood of this other data point here shown in green under the model that we have learned, but we can also sample from this distribution. And this is what I show here on the right-hand side. And what is crucial here, especially when we look at the samples, is to highlight the fact that we want our models to generalize, right? So I specifically shown some model samples that have the same statistical properties as the data, but they're not exactly the data, because otherwise I can just use a lookup table. So this is just a high-level motivation of what we want to do with this. And if we think of machine learning data, one example that I'm also going to use throughout the talk is, let's say we have a data set of faces, of pictures of human faces. Then if I think about what I would like from a model, when I sample from that model, I want to see a human face that is very realistic, but not a face that is seen before, maybe most likely a face of a human that doesn't even exist. So this is what we're interested in. And throughout the talk, I'm going to focus on doing this using neural networks. And the reason for that is that neural networks are very powerful function approximators, and they can be learned using scalable learning algorithms. So what do I mean by that? Well, the idea of powerful function approximators using neural networks is actually quite simple. And it's an idea that we will see also in the context of probability distributions. And the idea here is that we will take very simple building blocks and we will compose them to build quite complicated functions. And some of the simple building blocks can be linear operators, such as just matrix multiplication, or convolution operators that have these parameters that we're going to learn. So for example, we might learn a weight matrix. And they are followed by a nonlinearity that is not learned. So something like a sigmoid or a tanh or something like that. And the key idea is that when we compose these simple functions, we actually can get very, very powerful function approximators. And some idea of how powerful this function approximators is, let's think of one benchmark that has been used in computer vision in the last 10 years, which is ImageNet classification. So ImageNet is a very complex data set. It has a very high dimensional image with 1,000 different classes, which include volcanoes and people and dogs and so on. And we can just see that from 2011 to 2015, we went from 25% top 5% accuracy to below human error. And what has happened in 2020, which is perhaps even more interesting, is that now human raters actually prefer the labels provided by the models rather those provided in the data set. So these are very powerful models, but of course this example is a classification example, and I'm going to showcase this idea with generative modeling instead of supervised learning. I've also mentioned that we need scalable learning algorithms. So the reason for that is that a lot of these machine learning data sets are very, very large. And we cannot afford to have algorithms that are, let's say, on the third order in the size of the data set. So we want something that learns relatively efficiently in the size of the data, for example. But the kind of problems that we're going to look at, they're all going to look like that. We're trying to minimize a function L that will depend on the parameters theta. And we're going to do that using gradient descent. So we're going to take iterative updates to get to a local minima of this function L. Now, of course, there are some challenges that come with this. Our loss functions L are not going to be convex in parameters for complex neural networks. And then we cannot have any global convergence guarantee. So this is why I said we'll only be able to reach a local minima. But in order to be able to compute these gradient descent updates, we need to be able to compute the gradients of the loss function with respect to any parameter of our model. So this is why we have what in neural networks we call the forward and the backward pass. So the forward pass is just evaluating our function approximator, so our neural network, and that's just very easy. As we always do in function composition, we start with the input, we apply it on the first function, second function, and so on. But what's interesting is that with the gradient, so when we want to compute the gradient, let's say, of the loss function with respect to the parameters of the first layer, we will actually go from back to front. And the reason for that is actually quite intuitive. So computing the gradient of the loss function with respect to the output of the network is relatively simple because the loss function is a function that we have, and then the output is available after a forward pass. But then if we want to compute the gradient of the loss function with respect to, let's say, the parameters of the first layer, and this is what we call a layer, is what we call the first function in our chain of function compositions, what we will do is that we will use the chain rule, so something relatively simple, to rewrite this gradient as a gradient in terms of the activations of that layer, what we call the output of that function. And the reason they are called activations is just due to some loose similarities with how brains are being modeled. And then the chain rule tells us that we have to compute this gradient and the Jacobian of the activations with respect to these parameters, which are easy to compute, again, because each individual layer is very simple. And now once we have this relationship, we know that what we're interested in next is to compute the gradient of the loss function with respect to the activations. And again, we can use the chain rule, and we see that the gradient of the loss function with respect to the activations at the first layer depends on the gradients of the loss function with respect to the activations at the second layer, and so on. So if we want to then compute the gradients for each parameters, what we will do is we're going to go from the back, we're going to compute the gradient of each activations from the back to the front, and then use that to compute the gradients with respect to parameters. And this is what we use to then plug into the gradient descent updates that I've shown below. However, for the purpose of this talk, we can't think about neural networks just as a powerful function approximator that will be learned using this approach. So I'm not going to go into the detail of how each gradient might look for different network architectures, but we'll just treat them as a very large, flexible class of functions that we will learn using this approach. But what I'm going to focus on is, for example, what is the kind of loss function that we might use to learn this kind of generative model, and also how we will model this distribution as well. So that's going to be the second part of the talk. So let's talk about the objective that we're going to use. So what we're interested in is finding a measure of distance between distributions. So imagine that my true data distribution is here and my model is here. I would like something that tells us that, well, if I move a bit more to the right, so my model in blue moves closer to the data distribution, then I'm doing a little bit better. So what we're looking after is ways to measure distances between two different distributions. Now, there is a challenge here, of course, that in the problem of generative modeling, we don't have access to the true distribution. So we are looking for these distances that can be evaluated only using samples from the true distribution. Because if we have samples from the true distribution, then we can use unbiased estimates of functions that look like this. So if we have an expectation under the true data distribution of a function, we will just use the empirical mean to get an unbiased estimate of that quantity. So we are restricted from the set of all possible distances and divergences to those that can be evaluated using Monte Carlo estimation. And I've mentioned this idea of distances and divergences, and these are the kind of objectives that are often used in the generative modeling world. And these are they both have different properties, but what we are interested in is primarily from the convergence point of view, the idea that if a distance or divergence between two distributions is 0, then we know that the model has learned the true data distribution. And of course, this is not going to be the case in practice because the model might not be powerful enough to learn the true distribution, or because we only have, of course, samples from that distribution, but it allows us to construct some convergence guarantees, which are very useful. And of course, one of the most popular ways to learn generative models is to use the KL divergence. And again, the KL divergence is asymmetric, so the order matters. And specifically because of this constraint that we need to have our distances and divergences depend on the data distribution only through expectations. This is specifically important because the KL divergence, through some simple manipulation, can be written this way. And this means that if we want to minimize the KL divergence between the true data and the model, that is equivalent to maximizing the expected value under the data distribution of the log probability that the model assigns to the data. So this is both nice because now we have something that only depends on samples from the true distribution. So we will use Monte Carlo estimation to evaluate this. And of course, we do have samples. This was the problem statement that I started with. We assume we have samples from this distribution. And then it's also intuitive because it says, well, I want to learn a model that can explain the data, that assigns high likelihood to the data. But most recently, especially in the field of generative modeling using neural networks, there have been some new approaches, such as using two-player games to learn distributions. So this idea is, I find it quite intuitive. Instead of using directly divergence or distance as our loss function, we will have a neural network, what we call a discriminator, that learns to distinguish between real data and data generated by the model. This is what we call generated data or fake data. And you can think about this as it's quite reminiscent to sample tests, for example, but it's a parametric version of that. Of course, it has a lot less guarantees, but it is also cheaper to evaluate for and to use in gradient descent, as we will want to use for our model. So this brings me to our model, which in this context we call a generator. And the goal of the generator is to generate data that is so good that it fools this discriminator that it is real. So the idea here is that we have a bit of this cat and mouse game of we start with a generator that is not so good. Then the discriminator has a relatively easy task to distinguish between real and generated data. That allows the generator to improve a little bit. Then the discriminator has to improve a little bit in order to catch up, and so on, up to the point where we can generate good samples. And just as another view of this, so the discriminator, again, a neural network, is trying to answer the question real or generated, and we're going to see approaches to quantify this in a bit. And our model, the generator, is generating data that is now being fed into answering this question. So how do we actually go about quantifying this? Well, we are going to quantify this as a zero-sum game. So that means that whatever the discriminator gains, the generator will lose. So we will write this as this min-max problem, where the goal of the discriminator, as said, is to distinguish between real and generated data. And we can formulate this as a binary classification problem, where the data is being classified as real and the generated data is classified as fake. So this is just a binary cross entropy loss, with the difference that we now sample from our data and sample from our model. So here we have a Monte Carlo expectation to evaluate with samples from our model as well. So the discriminator in this case with parameters phi is trained to be a binary classifier. Now, the goal of the generator, remember, is to fool this discriminator. So it has exactly the same loss function, but with a change of sign, or the discriminator is maximizing the loss that the generator is minimizing. So the goal of the generator now is going to be to minimize the probability that the discriminator correctly predicts that the generated data is generated. So this is how we quantify what I've said before intuitively, that the generator is trying to fool the discriminator. And one natural question that you might have here, well, when we talked about distances and divergences, we said, well, we like having them because they give us some convergence guarantees about what the model is going to learn in an optimal setting. So one question that you might have as we present these adversarial games, often called generative adversarial networks, is, well, is this connected to distance and divergence minimization? And the answer is yes, under very optimal settings. So if the discriminator, the neural network that learns to distinguish between real and generated data, is optimal, then the generator is minimizing the Jensen-Shannon divergence between the true and generated distributions. And what's also very impressive here is that the Jensen-Shannon divergence is one of these divergences that we wouldn't be able to easily evaluate using Monte Carlo estimation, because it depends on the data distribution beyond having this form of a nice expectation. So that's quite nice. But GANs can be connected to a lot of other divergences and distances, and I just want to show just one more before we move to models, and that is the Wasserstein distance. So the Wasserstein distance has an optimization in its definition. So if I want to estimate the distance between two distributions, I have to compute the supremum over one Lipschitz functions of the difference in expectations under these distributions of these functions. So now, of course, the challenge is that this is intractable for complex distributions. So one idea here is to say, well, I'm going to use a neural network to approximate the supremum. So what we're going to do is we're going to use a discriminator. The discriminator will now become our function f, and the discriminator, as in the definition of the Wasserstein distance, it will try to maximize this difference in expectations, and it's going to be regularized. The neural network is going to be regularized such that it is one Lipschitz. So this is the goal of the discriminator, to estimate the Wasserstein distance, and the goal of the generator will be to minimize this estimate. And again, if the discriminator is optimal, you will have that the generator will minimize the Wasserstein distance between the data and the model. Now, of course, this view of GANs as divergence minimization is a bit misleading, because in practice, the discriminator is not optimal. So it's not optimal for many reasons. We might not have the right model. It might not be powerful enough to make this distinction between real and generated data. But more importantly, what we would have to do in these zero-sum games would be to, for each gradient descent update of the generator, we would have to train the discriminator to optimality, which is something that we cannot do. We cannot train a neural network to optimality for each update of another neural network, because that's going to be computationally very, very prohibitive. So what people do in practice is actually they alternate between the updates. But this is actually not necessarily a problem. And the way to think about this, I find, is to think of discriminator as learned distances. And I put distances in quotes because they are not satisfying the properties of a mathematical distance. But from the perspective of the generator, what the discriminator is, it's part of a learned loss function. And that is actually an asset. So if we think about the KL divergence, when we learn models on data or models on text, the KL divergence has no knowledge about the data modality that is being used. It's just trying to maximize a likelihood. The model might, so we might choose the type of neural networks that are good for text and good for images, and we're going to see some examples of that in a bit, but the loss doesn't. And what these kind of models like GANs do is that they build this knowledge in the loss function as well. So what do I mean by that? Imagine that I want to train a generative adversarial network on images. Then I will choose a discriminator, a neural network architecture that I know does well on images, something like a convolutional neural network. And what that will do is that if the generator generates, let's say, blurry images, the discriminator, who has inbuilt edge detection in, will be able to penalize the generator for generating blurry images and will force the generator to generate sharper images. And this is actually something that we see in practice. So this idea is just taking it one step further from having neural networks in the model. You can also think about it as having neural networks in the loss itself. So I mentioned the model and that it's going to be represented using a neural network, but I haven't really talked about the choices that we have to represent our models. And just to start with, of course, this choice is extremely important, because if we have a true distribution, let's say, as shown here in red, as a mixture of two Gaussians, but my model is going to be a Gaussian, I'm not going to be able to represent that distribution. And I might get, for example, as in the example shown on the left, a lot of samples from these distributions that have very low mass under the true distribution. Or I might completely overfit to the data and not be able to generalize. So we want to be somewhere in between. And it's very important to have that in mind as we will go, for example, through the next cases. But beyond going to concrete examples of choices of models, we have two broad choices that are all very much used in practice in the machine learning community. So one choice is, do I actually want to model the density P of X explicitly? Do I need to query this density once I am done with the model? And this is what we call an explicit likelihood model. Or I might say, well, actually, I'm not really interested in querying this model afterwards. I just want to be able to sample. And these models that don't model the density explicitly are called implicit generative models. The other choice that we have is whether or not we want to introduce auxiliary variables in our model. So for example, if I think of a data set of, again, images of faces, well, I might say, well, I'm just going to model the pixels individually. But what I can also say, well, images of faces have a very clear structure. So for example, if you look at a picture of me, you will figure out that, well, these pixels here on the left side are correlated with the pixels on the right side, because most of the time when people wear glasses, the glasses are of the same color. So one intuition that you can have here is that, well, perhaps this very high dimensional data is embedded on a lower dimensional space. And I can, instead of learning a likelihood over that high dimensional space directly, I can actually learn a mapping from a low dimensional space to a high dimensional space. And that's where, for example, our neural network is going to be. And we're going to talk about that in a bit. So let's look at some concrete choices that, for example, are explicit or may not introduce latent variables. And one explicit model that is especially popular for, let's say, on text data are what we call autoregressive models that use the product rule of probability. So they say, well, the likelihood that I see a particular image is the likelihood that I see the first pixel times the second pixel given the first pixel times the probability that I see the third pixel given the first two, and so on. And the way we model this using neural networks is that the neural network is going to model the conditional probabilities in this case. And what is very crucial here is that actually we don't have a different neural network for each conditional probability. There are types of neural networks, which we call these autoregressive models, that can model variable length input. So we will actually share parameters for all these conditional distributions require to model our data. And this idea of parameter sharing is actually quite an important one in general in machine learning, but specifically also here in the case of generative modeling. And these kind of distributions, they are very expressive and they're very powerful models. But the challenge is that if you want to use these models to sample from them, so let's say you've trained a generative model of text and then you want to sample an article, let's say on a Wikipedia article, it's going to be very slow because it's of the order of the number of tokens in your data. So you'll generate the first word and the second word given the first one and so on, which can be very slow. But there are ways these days to speed this up as well. Now, another approach that is very much used most recently in machine learning is to use normalizing flows. And normalizing flows have this idea of using the change of variable formula to model distributions. So we can start with a very simple distribution, like a Gaussian distribution, and then I can apply an invertible function to transform that random variable. And then I can use the change of variable formula to have the density of the new random variable y. Now, there are two challenges that come with this in the context of machine learning and in the context of using neural networks for these type of models. The first one is that neural networks are not invertible functions. So there has been a lot of work in the last 5 years trying to figure out how to make neural networks be part of building blocks that are invertible, or constrain them in such a way that they are invertible, for example, making them by Lipschitz and so on. But there is another challenge. The challenge comes from this determinant of the Jacobian term, because if we train this model, we will need to evaluate this likelihood for each training update. And we want this to be relatively cheap to compute, because otherwise it's just going to make these models very prohibitive to train. So this is an idea that comes again and again in machine learning, that you want to be cheap to train, especially in a gradient descent setting. So often what is done is, for example, you might restrict the family of transformations so that they are very simple. So for example, maybe even affine transformations, so that you can compute this determinant quite cheaply, and then use the very nice fact that if you compose very simple transformations, you can get, again, very complex ones. So this is exactly the same idea from neural networks brought in probability distribution. So if I compose one normalizing flow with another normalizing flow, I still get a normalizing flow. And even though each individual flow might be relatively simple transformation, I can compose them, let's say in this case, 10 times and go from a unit Gaussian to something that is quite a complex distribution. And actually in images, for example, these days we often go up to 100 layers of invertible transformations if we want to model something like a data set, a relatively small data set of images, actually. Now, one other idea that I talked about was this idea of using latent variable models. Now, there are also challenges with this. As always, we have the challenge that neural networks, while they are expressive, they introduce the challenge of making certain things intractable. So if I want to learn an explicit model that has a latent variable, what I have to do is to use the sum rule of probability and to say, well, this marginal distribution is this integral over this conditional model that I'm going to model using a neural network, and the prior, that it's something of my choice, something like a multivariate Gaussian. Of course, this becomes intractable very, very quick. So this can be done, for example, using PPCA for very simple linear models. But if you have neural networks, this is something that we cannot compute. And one is done in practice, and I'm just not going to go into the details of this, but a bound is introduced, and this bound itself introduces another distribution, which again we will use to approximate using a neural network. So the reason I wanted to highlight this is that we see in multiple situations, both in the GAN world and here in the world of explicit distributions using latent variable models, often when we see that something is intractable, we either introduce a bound or an approximation, and we use the power of function approximators of neural networks to get around that intractability. And this is something that in machine learning we can see again and again. And of course, another approach to get around this problem of this intractability is to say, well, actually, I don't really want to have access to the explicit likelihood. I just want to be able to sample from this model. And in that way, you can say, well, I'm just going to model the sampling path. So I'm going to have a latent variable. I'm going to produce a sample from its distribution, let's say from the Gaussian. That's something that is very easy to do. I'm going to pass that. That's going to be the input to my neural network. I'm going to pass that through the neural network, and that's going to give me a sample from my model. Now, the challenge here is that it also restricts the number of training criteria that you can use. Because when we saw maximum likelihood, we saw that you have to have access to the log density for training. So each of these model choices actually often come with a restriction of what kind of objective you can use to train that model. And often these type of implicit models, as we will see in a bit, are very used in GAN training. And often when you read one of these papers, they will present choices of the objective. So as I've shown before, is it the divergence? Is it a distance? What is the loss function? Is it something that we use via two-player game, something like a GAN? A choice of model. Is it explicit, implicit? Is it autoregressive? And a learning choice. So what I talked about early in the talk of this idea of using backpropagation, which is something that these days is pretty much implied in the field. And let's look at an example that kind of ties these choices together. So as I said, often GANs are trained as latent variable models. So when I presented them in the most general setting where you have any kind of model. And actually, we have a paper where we use an autoregressive model on text with this loss function. So it's not imply that you have to use an implicit model, but this is what is often done in practice because GANs only require samples from the distribution, and implicit models can do that very well, and they get around this challenge of intractability of the sum rule. And moreover, if you look, for example, at the original GAN paper, it will look something like this, where it will also show you the gradient updates that this loss function and this choice of model with particular latent variable will give you. The only thing that if you look at this will look maybe a bit scary is that you'll think, well, now I have to implement, let's say, if you want to code this, the backpropagation rule. So every time I change my model a little bit, let's say my neural network architecture, I have to change the backward pass. But luckily, this is no longer the case. So with modern frameworks, especially with frameworks such as JAX, this is done for you automatically. And specifically, the reason I want to highlight JAX, especially for this audience, is that it's very much in line with the mathematics and how we should be thinking about these things, which is that in JAX, if I have a loss function, which is, let's say, the discriminator loss function, I can actually ask JAX, okay, give me the gradient function of this function, and it returns me a function. So this is something that you yourself don't have to implement. You don't have to implement gradients in these modern tools. And then once you have this function, you can say, well, I evaluated at the discriminator parameters and generator parameters, and you use this in your gradient descent updates. So these days, unless you're doing something more complicated, which is still sometimes the case, you pretty much only have to concern yourselves with the forward pass, and then the backward pass pretty much comes for free implementation-wise. And let's talk a bit about some applications. I mentioned that we often talk about very high dimensional spaces when we talk about these models. And in the last, especially 2-3 years, we've seen a lot of progress in this space. So for example, I talked about implicit latent variables and GANs, and these are samples. So these are not pictures, they are samples generated by a model trained on ImageNet. And it's able to generate these very high dimensional samples at high quality, something that was really not possible 5 years ago. We also have very good models of text. As I've said earlier, text models are often autoregressive because of the sequential nature of language, and they can be used for not only to model language, but turns out they're very useful for a lot of downstream tasks, such as translation, summarization, question answering. So actually, a lot of the reasons why people train these generative models is, for example, to get the representations out of these models and use them for downstream tasks as well. So there are many other reasons why you might want to go, let's say, through the trouble, and this is a very difficult task often, to learn a generative model of image or text. And there are also types of applications that have been unlocked using these new types of research, including unsupervised image-to-image translation. So this is one of my favorite ones, and it's a lot of fun, in that if you think that you have let's say, a picture of a zebra and you want to turn that into a picture of a horse, in the past you often would have needed paired data. So you would have needed a picture of horses sitting in the same exact positions as the zebras, which would have been very prohibitive, especially if we think of other types of things that we might do, such as turn Monet paintings to photos, because we might not know where Monet had painted that, or that place might not exist. But with this kind of methods that we've seen, we can actually go ahead and do that, for example, using GANs. And that's it for me. I hope I gave a very broad introduction of what people in machine learning have been doing using these ideas of distance and divergence minimization, as well as two-player games, and how they have been using neural networks to model these distributions, either explicitly or implicitly. Thank you.
Thank you very much, Mihaela, for a very interesting presentation. We have received a few questions submitted by the audience, which can be accessed through the Q&A box. I'll try to read some of these live and answer these where possible. I guess the first one is, in the introduction to generative adversarial networks, you mentioned that you approach the problem using a zero-sum game. Why is this? Is there an intuitive reason, application, as to why this is appropriate?
Yeah, that's a very good question. So actually, not all GANs are zero-sum. And I think it is quite intuitive that you want to have an adversarial setting. So that is the key idea, that you have a situation where if the discriminator gains, the generator loses, so that the generator has an incentive to become better. But they don't need to be necessarily a zero-sum. The zero-sum setting is quite intuitive if you think, what is the most adversarial situation that I need to get into? And this is how the original GAN started, but actually often there are GANs that are not zero-sum and used in practice. And the reason for that is actually not necessarily that people don't like zero-sum games, but more like the kind of properties that the losses themselves have. And when we talk about that, we always talk about the gradient properties of the losses, because we always talk about gradients in machine learning, because that's what we need to train.
Excellent. Thank you very much. What is the ON complexity of such algorithms and the amount of time they take to compute?
Right. So I think it depends on the algorithm. Is it the algorithm? You mean the gradient descent algorithm, or I think this it really depends on the exact algorithm that we are talking about. I think the key thing about these approaches is that, for example, if you take something like some more traditional machine learning approaches, some can be on the third order and in the data set dimension, which is not possible for ImageNet at all. And some of these machine learning algorithms, we're talking, I think you do linear passes, a few hundreds, so it's almost linear in the data set dimension, but of course it depends on the problem.
Thank you. And finally, since KL divergence is not symmetric, how do you decide the order of the distributions?
Yeah, this is a really excellent question. So one is a very practical reason, which is that the KL divergence in this way that I showed it, the maximum likelihood way, can be easily evaluated. If you do it the other way, then you depend on P theta in a way that cannot be evaluated using Monte Carlo estimation. You depend on P star. So you will depend on the true data distribution in a way that you can't compute. And this is where GANs come in, actually. So there are GANs that can be used to approximate the KL the other way. And the other way to answer this is that often these KLs are called the mode seeking or the mode spreading KLs. So it also depends on what you are trying to do. So for example, in the example that I showed with two Gaussians, what the maximum likelihood KL, so the KL between the data and the model, will do is that it will spread mass between the true distributions, while the other KL will focus on one mode and forget about the other. So it depends on what you care about as well. And it's this is a really excellent question. It's very important when we do these choices to know what are the trade-offs that come with these distributions.
Excellent. We actually have a few more questions, and I think we do have time to answer. So the examples at the end bring to mind deep fakes. Is the potential risk to society of such powerful algorithms something that is being addressed a lot in the research community?
It is starting to become addressed, yes. I think that there's a lot of work both on the ethical side, but also on the technical side to try to detect deep fakes. There's been a field now, I think it's called research forensics, where they are trying to detect these models, because even for the samples that are not distinguishable from real samples to the human eyes, there are still statistical artifacts that can be used to detect some of these. And of course, there's a lot of work in trying to advertise, for example, cryptography, because this is a solution that we know I can sign with my private key. Okay, this is something that Mihaela said, and then we try to build trust in that way. So there's a lot of work into using existing solutions such as cryptography, but also building new solutions, and also awareness and ethical work as well. But of course, with this kind of work, there's always more that can be done.
Excellent, thank you. And finally, is there much research into the variance of these model estimates in this setting, such as confidence bands? I understand that it is easy to see how well the model performs when looking at the outputs, but in large-scale applications, this may not be possible.
Right. So there is some work going into this. I think it's interesting. I think a lot of the focus on the community right now is also variance to training conditions. So variance between, if I train the same model twice, there's a lot of work on, do I get the same result? And different models are more known to be more stable than others. So for example, with GANs, for the longest time, if you use different initialization for your model, you would get very different results. So there is a lot of work into that, into the specific models of the variance of the outputs of one particular model. There's been some work looking at some of the challenges that come even with the good generative models that we have. And if there's interest in that, I can point to some papers.
Excellent. Thank you very much, Mihaela, once again, for a very interesting presentation and for addressing all of the questions received.